ground fault circuit interrupter, or GFCI, is a safety device designed to quickly break an electrical circuit when it detects a ground fault. A ground fault occurs when electrical current flows through an unintended path, such as through a person's body to the ground. A high-pot test, or high-potential insulation test, is performed to check the integrity of insulation by applying a high voltage to the device being tested. Leakage current refers to the small amount of electrical current that can flow between two conductors that are not intended to be connected. The weight of the woman and the block drain caused the water to accumulate in the shower pan, potentially creating a more conductive environment. The forensic engineer theorized that the close spacing between the neutral and ground contacts in the lamp's receptacle handle led to leakage current under high humidity conditions. This leakage current could have energized the entire lamp, including the reflector that the victim touched. The leakage current could have also prevented the GFCI from tripping in a timely manner, as it may have been overwhelmed by the increased current flow. The forensic engineer's theory is based on the assumption that the close spacing between the neutral and ground contacts caused leakage current, which energized the lamp and contributed to the electrocution. All theories in forensic cases are subject to scrutiny and further investigation. The case ultimately rests on the credibility of the forensic engineer's findings and the interpretation of the evidence presented in court. It's important to understand how GFCIs work and what factors can affect their performance. A GFCI constantly monitors the current flowing in the hot and neutral conductors of a circuit. Under normal conditions, these currents should be equal. If a ground fault occurs, some of the current will flow through an unintended path, creating an imbalance between the hot and neutral conductors. The GFCI detects this imbalance and quickly trips the circuit, cutting off the power and preventing electrical shock. Several factors can affect a GFCI's performance. Firstly, the GFCI itself can malfunction. Like any electronic device, a GFCI can fail over time or due to manufacturing defect. It's essential to test GFCIs regularly to ensure they are functioning correctly. Secondly, the presence of leakage current can interfere with the GFCI's ability to detect a ground fault. Leakage current is a small amount of current that flows through the insulation of electrical conductors. While it's usually not dangerous, excessive leakage current can create a false reading that prevents the GFCI from tripping in a timely manner. Thirdly, the type of ground fault can affect the GFCI's response. A direct ground fault, where the current flows directly to ground, is usually detected quickly by the GFCI. However, a more subtle ground fault, where the current flows through a resistance, may be more difficult for the GFCI to detect. In the case described, the forensic engineer theorized that the close spacing between the neutral and ground contacts in the lamp's receptacle handle created a path for leakage current under high humidity conditions. This leakage current could have energized the lamp and made it more likely that the victim would receive an electrical shock. It's also possible that the leakage current interfered with the GFCI's ability to detect the ground fault, delaying the tripping time. The NEC, or National Electrical Code, provides guidelines for the installation and use of GFCIs. Section 210.8 of the 2014 NEC requires GFCI protection for receptacles in dwelling unit bathrooms, garages, and outdoor locations. This requirement is intended to reduce the risk of electrical shock in these areas. Section 406.9 of the 2014 NEC covers the installation of receptacles in wet locations. It requires that receptacles installed in wet locations be weatherproof and have an enclosure that is designed to prevent water from entering the receptacle. There are several types of high-pot tests, each designed to test different aspects of insulation integrity. One common type is the alternating current, or AC, high-pot test, which applies an AC voltage to the device under test. Another type is the direct current, or DC, high-pot test, which applies a DC voltage to the device under test. The choice of which type of high-pot test to use depends on the specific application and the type of insulation being tested. During a high-pot test, the voltage is gradually increased until it reaches a predetermined level. This voltage is then held for a specified period of time. If the insulation is in good condition, it will be able to withstand the applied voltage without breaking down. However, if the insulation is weak or damaged, it may break down, causing a surge of current. This surge of current indicates that the insulation has failed the high-pot test. High-pot tests are used to detect a variety of insulation defects, including cracks, pinholes, and contamination. They are also used to verify that the insulation meets the required specifications. High-pot tests are typically performed as part of a quality control program. They are also performed during the installation and maintenance of electrical equipment. It's important to note that high-pot tests can be destructive. If the insulation fails the test, it may be damaged beyond repair. Therefore, high-pot tests should only be performed by qualified personnel using calibrated equipment. In the case described, the forensic engineer performed a high-pot test on the hand lamp to check the integrity of the insulation. The test revealed that there was a close spacing between the neutral and ground contacts of the receptacle in the handle. This close spacing could have allowed leakage current to flow between the neutral and ground conductors, potentially energizing the lamp and creating a shock hazard. The engineer's theory is based on the principle that electricity always seeks the path of least resistance. In a normal electrical circuit, the current flows through the intended conductors, such as the wires that connect the power source to the load. However, if there is a path of low resistance available, some of the current may flow through that path instead. In the case of the hand lamp, the close spacing between the neutral and ground contacts could have created a path of lower resistance than the intended conductors. This could have allowed some of the current to flow through the lamp's housing, energizing the lamp and creating a shock hazard. The engineer's theory is also supported by the fact that the GFCI tripped. This indicates that there was a ground fault in the circuit. A ground fault occurs when electricity flows through an unintended path to ground. In the case of the hand lamp, the ground fault could have been caused by the leakage current flowing through the lamp's housing. It's important to note that the engineer's theory is just one possible explanation for the electrocution. Other factors may have contributed to the accident, such as the condition of the electrical wiring in the house, the presence of other electrical appliances in the bathroom, and the victim's health. However, the engineer's theory provides a plausible explanation for the electrocution based on the available evidence. The use of GFCI protection is an important safety measure that can help to prevent electrical shocks. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. However, it's important to remember that GFCIs are not foolproof. They can malfunction or be bypassed. Therefore, it's important to take other precautions to prevent electrical shocks, such as avoiding contact with electrical appliances while wet and using properly grounded equipment. When investigating electrical accidents, it's important to consider all possible causes. This includes examining the electrical equipment involved, the wiring in the area, and the conditions at the time of the accident. It's also important to interview witnesses and gather any other relevant information. Forensic engineers play an important role in investigating electrical accidents. They have the expertise to analyze the electrical systems involved and determine the cause of the accident. Their findings can be used to prevent similar accidents in the future. The 2014 NEC provides detailed requirements for electrical installations. These requirements are intended to ensure that electrical systems are safe and reliable. It's important for electricians and other electrical professionals to be familiar with the requirements of the NEC. The NEC is updated every 3 years. It's important to use the latest version of the NEC when designing and installing electrical systems. In addition to the NEC, there are other standards and guidelines that can be used to ensure electrical safety. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. Electrical safety is a shared responsibility. Electricians, engineers, homeowners, and others all have a role to play in preventing electrical accidents. By following safe electrical practices, we can reduce the risk of electrical shocks and fires. It is also crucial to select the right type of GFCI for the application. There are different classes of GFCIs designed for specific purposes. For example, Class A GFCIs are designed to protect people from electrical shock, while Class B GFCIs are designed to protect equipment from damage. It's important to choose the right class of GFCI for the application to ensure adequate protection. Regular testing of GFCIs is essential to ensure they are functioning correctly. GFCI should be tested at least once a month using the test button on the device. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. Proper installation of GFCIs is also critical. GFCIs should be installed by qualified electricians in accordance with the NEC and manufacturer's instructions. Incorrect installation can compromise the GFCI's ability to protect against electrical shock. Education and awareness are key to preventing electrical accidents. Homeowners and workers should be educated about the hazards of electricity and the importance of safe electrical practices. Training programs and public awareness campaigns can help to promote electrical safety. Electrical safety audits can help to identify potential hazards and ensure that electrical systems are in compliance with safety standards. Audits should be conducted by qualified professionals on a regular basis. The use of personal protective equipment, or PPE, is essential when working with electricity. PPE includes items such as rubber gloves, insulated tools, and safety glasses. PPE can help to protect workers from electrical shock, burns, and other injuries. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned back on. Emergency response plans should be in place to address electrical accidents. These plans should include procedures for providing first aid, contacting emergency services, and securing the area. Continuous improvement is essential for maintaining a safe electrical environment. By regularly reviewing safety practices, identifying potential hazards, and implementing corrective actions, organizations can continuously improve their electrical safety performance. In summary, the forensic engineer's investigation highlights the importance of GFCI protection and the potential hazards associated with leakage current. The close spacing between the neutral and ground contacts in the hand lamp could have created a path for leakage current, energizing the lamp and contributing to the electrocution. The investigation also underscores the need for regular testing and maintenance of electrical equipment, as well as adherence to safe electrical practices. By taking these precautions, we can reduce the risk of electrical accidents and protect ourselves from electrical shock. Always consult with a qualified electrician for any electrical work or repairs. Electrical work can be dangerous, and it's important to have it done by someone who is trained and experienced. Never attempt to repair electrical equipment yourself unless you are a qualified electrician. When working with electricity, always follow safe electrical practices. This includes avoiding contact with electrical appliances while wet, using properly grounded equipment, and wearing appropriate personal protective equipment. Be aware of the hazards of electricity. Electricity can be dangerous, and it's important to understand the risks involved. Take precautions to protect yourself and others from electrical shock.